Thank you very much. Thank you very much for the invitation. I'm sorry I couldn't get to Connecticut, but it's still the semester going on here, and making just an overseas trip for just 3 days is too little. I think you can see me, right? So just to be in the mood, I put up this shirt today. I mean, so virtually I'm there, right? Okay, so this is some recent joint work we made with Anton Freund, who recently moved to Würzburg, Germany, and with Fedor Pakomov and Giovanni Solda, who are in Ghent, Belgium. And so this is still work on better quasi orders, which better partial order and better quasi orders, which those of you that know my research have been a constant topic throughout my research. So the plan of my talk is to start telling you about what the WPOs and BPOs are. And so even maybe the younger people who don't know this notion will learn that, hopefully. And we will concentrate especially on finite better partial orders. And we will mention some results. I will mention some recent results by Anton Freund, especially, that have really changed a little bit the situation there. And so in this context, I will be able to prove about this provable better partial orders of my title. And I think I will be able also with those results to explain you what we got about different versions of a so-called minimal better array lemma, which is a basic tool in better partial order theory. And if time allows, if I have time, well, I'll try to sketch one of the main proofs of our work. So, okay, let's start with well partial order and better partial orders. So first, well partial orders. We have a partial order P, and we say that it's a well partial order if satisfies the following condition. Whenever you have a sequence of elements indexed by the natural numbers of elements of P, you will be able to find I and J, indices I and J, such that I is before J, and f of I, the ith element in the sequence, is P below the jth element in the sequence. This might at first look, if you haven't never seen this, a little bit strange, but it's actually a very important notion. And this is also shown by the fact that you can characterize well partial order in several different ways. And among the characterization of WPOs, let me mention the following. The first one that usually is given also as a definition is that the partial order must be well-founded, so no infinite descending chains, but also no infinite anti-chains. So it must be well-founded, but also not too wide, let's say. Another characterization of well partial order that you can take as another definition is that you take a sequence in P as before. Not only you can find those two specific indices I and J, but you can actually extract a subsequence which is weakly increasing. So the ith element is below the next element, which is below the next element, and so on and so forth. Another characterization, well, if you have a just well-founded partial order, every non-empty subset of a partial order will have a set of minimal elements. Since we are also asking no infinite antichains, that set of minimal elements is an antichain and so should be finite. So a characterization of well partial orders is that every non-empty subset of P is a finite set of minimal elements. And also, another characterization, you look at linear extension of P. You have a partial order. There are different ways of linearizing it, of extending it by adding more comparabilities to make it a linear order where everything is comparable with everything. And if you start with a well partial order, then no matter how you perform with this linear extension, this is going to be a well order. So all linear extension of P are well orders. It's another characterization of well partial orders. And the equivalence between all these notions is actually showing that we have a very significant notion that it's worth studying. And well, from the reverse mathematics point of view, we started studying the equivalences between this, and this has been studied quite in detail, starting from a paper in 2004 with Peter Cholak and Reid Solomon. And well, just let me say that as an upper bound, all the equivalences are provable in WKL naught plus the chain anti-chain principle. So you need these principles. So for some of them, you need WKL naught, for some CAC, and there are different situations there, but I don't want to go more in detail into this. Some reverse mathematics of WPOs, just to get you a little bit in the frame of mind that we are dealing here. Well, first of all, it's easy to show that in RCA naught, you can prove that finite posets are well partial orders, and also that well orders are well partial orders. Here for well partial order, I mean my original definition, the definition with a sequence and just two elements in the sequence that are comparable in that prescribed way. On the other hand, already in the 1980s, Simpson and Claude, putting together the result, showed that ACA naught is equivalent to the following statement, which is what is usually called Higman's theorem. That if you start from a well partial order and you form finite string from the partial order under a very natural embeddability relation, then this relation will also be a well partial order. So this is a sort of a most basic theorem in well partial order theory, and it's actually equivalent to ACA naught. But well partial orders were also used to show that some results that are quite easy to state are actually not provable in even quite strong theories. So I'm thinking of these two theorems. Harvey Friedman is involved in both of them. The first one, 1985, is that ATR naught is not able to prove Kruskal's theorem. Kruskal's theorem is asserting that a certain notion of embeddability between finite trees is actually a well partial order. And Friedman exploiting, sort of coding into these finite trees appropriate ordinals show that ATR naught cannot prove this result. Let me mention here that a result such as Kruskal's theorem cannot actually imply ATR naught or any strong theory, because being a WPO is a pi-1 notion, because you are just saying for every sequence something finite happens. And so it doesn't carry any, set existence property. You can just prove for a statement like Kruskal's theorem, a result like the one by Friedman, that it's so complicated that ATR naught is not enough. So this is clearly an instance of a real theorem which is not provable in a quite strong theory as ATR naught. And a few years later, Friedman, joining with Robertson and Seymour, proved that pi-1 comprehension, so an even stronger theory, is not enough to prove a so-called graph minor theorem. The graph minor theorem is talking about finite graphs and look at the minor relation, which is a basic relation studied by graph theorists. And Robertson and Seymour at the time were actually proving the graph minor theorem. The proof of graph minor theorem quite famously took, I believe, 23 papers to be written out completely. But even when there were just a few of these papers out, they joined with Harvey Friedman and showed that pi-1 CA naught will not be able to prove even the sort of a sub case of a graph minor theorem they had already proved at the time. And so pi-1 comprehension surely cannot prove the full graph minor theorem that came, whose complete proof came a few years later. So we have these results about WPOs. I'm also, well, one of the most famous results about WPOs, and joining also with better partial order, it's a way of introducing better partial orders for me, is Frazès conjecture. So Frazès conjecture, which came back from the 1950s, is the statement that if you look at embeddability on countable linear orders, then there will be a well partial order. And this was proved a few years later in the early 70s by Lever. And Lever's theorem is proved that actually Lever proved something more, proved that embeddability on countable linear orders is a better quasi-order. Here I'm talking about quasi-order rather than partial order, because there might be B-embeddable linear orders which are not the same. So it's antisymmetry fails, and that's the difference between a partial order and a quasi-order, but it's essentially the same thing. So I still keep it distinct from Lever's theorem because, well, these are two different statements. The second one involves better partial order, which I introduce in a few slides. But the point here is that also we don't know, we have no proof of Frazès conjecture without proving Lever's theorem. And from the axiomatic point of view, the best proof of Lever's theorem we have is one given by Antonio Montalbán a few years ago, 2017, when he showed that pi-1 comprehension actually suffices to prove Lever's theorem and also Frazès conjecture. And it's still open whether the exact classification of Lever's theorem, the lower bound, is given by a theorem of Richard Shore, 1993, that Frazès conjecture implies ATR naught over the weak base theory RCA naught. So we have still this gap, and if we look at Frazès conjecture, we see that that actually it's a pi-1,2 statement here, because the comparability, the embeddability notion is sigma 1 itself. So being pi-1,2 cannot imply pi-1 comprehension by general facts. So the classification for Frazès conjecture is sort of a greater than or equal ATR naught, but surely not able to get to pi11 comprehension, but it's still an open problem even after Antonio's progress made a few years ago. So this is about Fresnel's conjecture, and let me start introducing better partial orders. So this is a notion that was introduced by Nash-Williams in the 1960s. It's a strengthening of well partial orders, as I implicitly already mentioned, because I was discussing Fresnel's conjecture and Lava's theorem as a strengthening of Fresnel's conjecture. And it's a bit technical, but since I will be talking about better partial order, I felt we needed to give a complete definition of better partial order, which will take a few minutes to be introduced here. So the general idea is that the property of being a better partial order is preserved by more operations than those that preserve just the property of being WPO. And this is helpful when you try to prove that something is a well partial order. Actually, sometimes it's easier to prove that it's a better partial order because of these better closure properties. And the general pattern is that if well partial orders are closed under a finitary operation, the better partial orders will be closed under the infinitary generalization of that finitary operation. And this is shown by this theorem of Poussin, 1972. You take a poset, a partial order, and the following conditions are equivalent. P is a better partial order. The second condition is that you look at countable transfinite sequences of elements of P under the embeddability notion. We were already discussing finite sequences of elements of P, and the embeddability notion is essentially the same, but here you admit infinite and in fact countably transfinite sequences, and this is a WQ. Again, I have to write this quasi-order because there might be B embeddable sequences which are not the same. And so while and the third condition is essentially the same as the second one, except that I'm talking about better partial orders here rather than a well quasi-order here. So essentially the equivalence 1 and 3 is the closure of better partial orders under this forming these transfinite sequences, countably transfinite sequences, while the equivalence between 1 and 2, if you want, you can take it as a definition of better partial order because it's not self-referential. In 2, there is no mention of the notion of better partial order, but it's not a very useful definition, in fact, because it's not very useful, very easy to, it's not easy to work with this notion, but you can view it in this way. So that's the way also better partial order arises. So we want to give a definition of better partial order, which actually can be used in practice. So here is my slide for the definition, which has several steps. First, I just fix some notation. So I'm talking of finite sequences and also infinite sequences of length omega of elements from some set X, which is a subset of the natural numbers. And we identify these sets with I'm talking about sets. I think I said sequences, but I meant sets. So finite and infinite subsets of some subset X of the natural numbers. And it identifies these sets with a strictly increasing sequence enumerating them. And when we write with a square bracket between S and T, the square bracket inclusion between S and T, this means that S is a proper initial segment of T, is a prefix of T. So the first few elements of T are actually the elements of S. That's essentially what we're saying. When I use the normal inclusion symbol, I mean that S is a proper subset of T really as a set. It means that maybe in S, the first element of T is missing, but when there are a few elements of T, some other elements are missing, a few more elements of T, and then S is done like that, but consists only of elements of T. So obviously the square bracket relation implies the inclusion relation. Now, the basic definition for getting to better partial order is this definitions of block and barrier. So we have a collection of finite strictly increasing sequences or of finite sets. We say that P is a block if, first of all, we want that B mentioned enough numbers, essentially. This is a collection of finite subsets of numbers, so the union of B must be infinite. That's the first condition. But then the key condition is that if I take any infinite subset into the union of P, then you will find in B an initial segment of X viewed as an increasing sequence, which belongs to B. And there is actually only one of those, just one for every X. So that means that if you take two different elements of B, one cannot be an initial segment of the other. So the set B is prefix free by using some terminology, which is maybe more used in computer science. So this is what is a block. And you see from here that this is already a pi-1 notion, because you are asking that for every subset of this union of B, for an infinite subset of a union of B, something happens. And so it's a pi-1 notion. A barrier is a special kind of block, because you don't ask only that the set is prefix free, but you ask also that it's subset free, let's say. So that if you have two elements of B, then it's not possible that one is a proper subset of another one. And so this will be a barrier. And our definition of better partial order will use these barriers. And a P array is a function that goes from some barrier into P. So it's like a sort of sequence of elements of P, but indexed by a barrier. Let me point out that among all possible subsets of N, obviously, finite subsets of N, there are the singletons. So now, if you look at the collection of all singletons, this is easily seen to be a barrier. So actually, the sequences indexed by numbers, by omega, which we're using in the definition of well-partial order, are a special kind of P arrays when we identify an element with its singleton, a number with its singleton. So we are still looking at a generalization of those sequences, more general sequences here. Now, we just use this notation. X minus is the infinite set X, or even finite set X in some cases, with the first element, the least element removed. And the triangle relation, which is one of the basic tools here, is S triangles T if S is an initial segment of some infinite set X, and the T is an initial segment of X with the first element, with the least element removed. And actually, even if my definition here in the first line of this bullet point actually involves the existence of a set X, potentially infinite set, actually, this is something that we can decide very easily, because it's just a little bit more difficult to write the actual definition, but we can just look at S and T, at the union of S and T, at the elements mentioned by S and T, to recognize whether S is in the triangle relation of T. So to get you some idea about this, let me just make an example. So I can say, I don't know, that the sequence 1, 3, well, I was hoping this would write in a better way than it's doing now. No, I cannot manage to write a number here. What's going on? I don't know. Okay. Well, it's not working the way I expected it to work. So let's forget about it. Let me just say that 1, 3 is in the triangle relation with, say, 3, 4, 5, which in turn is in the triangle relation with 4, 5, 6. So we have from Y3 to 3, 4, 5 to 4, 5, 6, but it's clear that 1, 3 is not in the triangle relation of 4, 5, 6. So this triangle relation is not transitive, except on singletons. While on singletons, actually, it's the same as the usual order relation when we make this identification between numbers and singletons containing them. So singleton N is in the triangle relation with singleton M exactly if N is strictly less than M. So the triangle relation is sort of an extension of a less than relation, which was also involved in the definition of well-partial order I gave before. And then we say that a P array, so remember a P array from a few lines above is just a function on a barrier with elements in P, is a good P array if you can find two elements in the triangle relation between them, such that the image of the first element is in the P relation, in the order relation with F of the second element. So again, if B were the barrier of singletons, this would be just the definition of a sequence which was behaving in a correct way with respect to the definition of well-partial order. And if a P array is not good, then we say that it's bad. And a better partial order, eventually I'm getting at the end of the slide, and so at the actual definition of a better partial order is it's a partial order such that every P array is actually good. So in particular, it includes that all sequences indexed by elements of omega behaves in the way prescribed by the definition of well-partial order, but more than that, because you are also considering p-arrays on very complicated barriers, which might be much more complicated than the barrier of singletons, which in fact is in a precise sense the simplest possible barrier. So this is the definition of better partial order. And let me notice that the definition of better partial order is pi12, because we are saying for every f and for every b, if b is a barrier, which we noticed was a pi1 condition, then there exist these two elements. So even if the elements s and t are finite, and maybe f of s and f of t are quite simple objects into this partial order, and the relation is quite simple, still this is pi12. So it's actually a more complicated notion than the notion of well-partial orders. Now, what about the basic reverse mathematics of better partial orders? Here we can get some very, very basic facts about partial order, better partial orders in RCA naught. For example, the sum of two better partial orders BPO. This, for the sum, I mean that I have a partial order here, P, let's say. Let's see if I cannot draw any letter. I don't understand why. And I have a second partial order here. Let's call it 2. Just that's the only thing that apparently I managed to write. So I'm putting every element of the first partial order below any element of the second partial order. I'm doing a sum just by putting everything in the first partial order below the second one. And if I do just this very simple operation, it's easy to see that RCA naught will preserve better partial order. If both of them were better partial order, also this sum is a better partial order. Also, another thing that you can prove in RCA naught quite easily is if you take a well order. Well, a well order is a linear order, but in particular is a very particular kind of partial order. And so this turns out also to be a better partial order. And as far as we know, not much more is possible to do in RCA naught. Well, let's see. Something more is a little bit more possible, but not much more. So, for example, in an old paper about 20 years ago, I try to look at what happens when we do the disjoint sum. So here the disjoint sum is I take the first poset here, another poset here, and I sum them in a disjoint way. I usually use this notation here with U plus, circle plus, basically. So that means that everything in the first partial order is compared as it was in the partial order. Everything in the second partial order is compared as it was in the second partial order, and I add no more comparisons between these elements. And proving that this disjoint sum is a better partial order is quite complicated. It's actually as complicated as showing that the product of two better partial orders is a better partial order. And at the time, I showed that any of those two statements actually implies RCA naught. So it's something that we cannot do even in RCA naught. We already realized this about 20 years ago. We will have some slight improvement of this statement later. But the idea is that even with respect to very simple operation, better partial orders can be a little bit harder to deal with. And so let's move as even finite better partial orders seem to be interesting from this point of view, because even just, well, a singleton is a better partial order because it's a well order, but just even looking at two incomparable elements seem to be interesting. And so at the time, I started looking at finite better partial orders. And okay, I mentioned that the notion of better partial order is pi12. It's actually pi12 complete. That's actually a theorem that goes back to my PhD thesis. And so even for a finite partial order, the statement P is BPO is actually pi12. And so it can carry potentially some set theoretic existence strength, some set existence strength. And so it's interesting from the reverse mathematics viewpoint. Well, as an upper bound, it's easy to see using the Clopen-Ramsey theorem, which is behind all what I will say that is doable in ATR naught, that any finite poset is actually a better partial order. So in ATR naught, we are able to prove that finite posets are a better partial order. ATR naught is our upper bound for everything, basically, I will say. But what can we do in theories which are weaker than ATR naught? So I will use this notation when n is a natural number. Just plain n means a chain of n elements. So it's a linear order is a well ordered with n elements, while n bar will be the anti-chain with n elements. So the elements, there are n elements and are pairwise incomparable. So that's a quite different situation. So in my old paper, I proved that the anti-chain with 2 elements is a better partial order. It's not a particularly complicated proof, but still it needs an argument. It's not something that you can do easily. And at the same time, I tried obviously at the time to prove that also the anti-chain with 3 elements was a better partial order, but I didn't succeed. What I was able to do at that time is that if I fix n greater than or equal to 3, then in RCA naught, if I know that this anti-chain with 3 elements, this 3 bar, is a better partial order, then I can prove that any poset with n elements is a better partial order. So I already noticed that there was, some sort of a big jump between 2 and 3 here. 2, I was able to do 2 bar. I was able to do in RCA naught. I wasn't able to do 3 bar, but I noticed that if I were able to do 3 bar, I would able to do essentially everything, at least in this form, that I fix n and I work in RCA0 for that specific n in this sort of non-uniform way. And so I asked the question, which was then asked again by Antonio a few years ago in his survey about open problems in reverse mathematics. What is the strength of this statement? 3 bar is a better partial order. So 3 bar again is the anti-chain with 3 elements. And well, I'm sure some of the people in the audience will remember that when I, had a chance to visit them or to meet them, or some of them were visiting me in Udine, I would ask, well, let's work on this problem. What is the strength of 3's BPO? And, we made several attempts. We made no progress whatsoever. And some of them probably got to hate this problem. But I was still asking this question many, many times. And eventually we got a progress. So last year, Anton Freund was able to prove that over RCA naught, 3 bar is BPO. So the statement that the anti-chain with 3 elements is a better partial order actually implies ACA0 plus, implies ACA0, but even ACA0 plus, which is a stronger theorem, still much weaker than ATR naught, but stronger than ACA plus. And in fact, using that proof, he was also able to prove the uniform version of what I proved many years ago. So in RCA naught, you prove that if 3 bar is a better partial order, then actually any finite poset will be a better partial order. So really, he's showing that 3 is much larger than 2, which is the title of the slide, and he's showing that there is really a big difference between 2 and 3. 2, at the level of 2, we are still in RCA naught, the anti-chain with 2 elements, or for that matter, well, any poset with 2 elements, there are just 2, the anti-chain and the chain. And instead for 3, for the anti-chain with 3 elements, we have a quite different situation. You have the strength at least of ACA0 plus, and moreover, once you have done that uniformly in RCA naught, you are done with any finite better partial order. So these are the only cases that are really interesting, is this gap between 2 and 3. And actually, when I visited Anton last December, he was still in Darmstadt. We actually noticed that you can strengthen a little bit his result, and you can show that ACA0 plus is not enough to prove that 3 bar is a better partial order. So our current knowledge about 3 bar is that it's strictly greater than ACA0 plus. I guess in Richard's degrees theory, it will be a degree which is strictly above ACA0 plus. It might still be the same degree as ATR naught, or maybe any degree which is in between ACA0 plus and ATR naught. We don't know the answer to that yet. So that's the situation for 3 bar is better partial order, and about what we know at the present stage. But once we also from this, it follows the statements like the disjoint sum of 2 better partial orders is a better partial order, which we already knew it implied ACA naught. It actually implies ACA0 plus, because if you have this statement, you can prove that 3 bar and even 4 bar, for example, is a better partial order in RCA naught, because you already know that the anti-chain with 2 elements is a better partial order. You put 2 of these, one on the side of the other, you get 4 or whatever. And so this must imply ACA0 plus, and actually cannot be provable in ACA0 plus. So we have also some strengthening of the strength of those statements. Now, after this this result by Anton Freund, we started thinking about this other question, which I think is very natural at this point. We have now examples of theories which do not prove that free bar is a better partial order. For example, ACA0, and even ACA0 plus. And RCA0, I mean, before Freund's statement, we didn't know that RCA0 didn't prove that free bar is a better partial order. So we have theories like that now. And then, so what posets can a theory like that is not able to prove that free bar is a better partial order can still prove to be a better partial order? This is similar to the question when you ask, well, you give a theory, this is a typical proof theoretic question, you are given a theory and you wonder what kind of well orders actually the theory can prove to be well orders, which kind of ordinals can be proved. So this is, provable well orders in a theory, and here we are talking about provable better partial order in a theory, and we can even restrict ourselves at least also just to finite better partial order, because if this is a theory that does not prove that all better partial orders, that all finite partial orders are better partial orders. So this is the question we are asking, and obviously, well, first, since there is this difference between 2 and 3, we start with the other posets of cardinality 3, and obviously, you can look at the chain 3, but that's a well order. So from what we know here, I managed to do this picture. So this is 3, but for some reason I cannot draw 3. I don't know. I cannot write 3. Okay, that's the chain 3 without any bar. That's clearly a better partial order even in RCA not. So there is no problem about that. Then I can look at 1 plus 2. So this will be made up of something like that. 2 elements, one here and one here, which are incomparable, and then an element below it. But this is just the sum of 2 better partial order, but the singleton better partial order, the anti-chain with 2 elements, even in RCA not. So that's clearly another better partial order. Then I can just look at the reversal of that, which is like that. So here I have 1 element on top of that, but I apply the same argument. It's the sum of 2 better partial orders, so it's a better partial order by what I said before. And there is only just one more candidate to look at, which is 1 plus 2. It's 1 element here on the side. Let's see if I can make it. Or 2 elements here. This is the 2. And then here, for some reason, it doesn't allow me to just draw a dot. Okay, here I have my dot. Okay, so this is 1 plus 2. It's 1 element and then a little chain of 2 elements, and these 2 are incomparable. This is 1 plus 2. And this does not follow from any of our results that this is a better partial order. So we start looking at this guy in particular. And what we found is that actually 1 plus 2 is already a problem for theories such as RCA not, because in RCA not, we can prove that 1 plus 2 is a better partial order if and only if the anti-chain with 3 elements is a better partial order. And so, for example, I say 0 plus does not prove that 1 plus 2 is a better partial order. So I went to my 12 years old daughter and said, well, we proved that 1 plus 2 equals 3, but for some reason she wasn't impressed at all. but I was impressed, I mean, by the result, and I'm talking to you about this. I hope you are more impressed than my little one. So 1 plus 2 really just behaves just like a free bar. One direction of this inequivalence, this equivalence is easy, because if free bar is a better partial order, it's easy to see that also 1 plus 2 should be a better partial order. But the other way is, if I have time, I will tell you something about the proof of the other direction, which is interesting. But once we learn this, we understand that really there is something here about 1 plus 2 and free bar. So we start looking at the partial order which do not have any copy of 1 plus 2 and / or free bar inside them. And we start looking at them because those are the ones that that are maybe provable to be better partial orders also when you are not able to prove that those 2 finite partial order are well partial orders. So our first result in this joint work with Anton, Fedor, and Giovanni is that in RCA not we can prove, well, we have to analyze these posets. So this is a proposition. We take a poset P and assume that it does not contain any copy of 1 plus 2 as a suborder. So you can never find 3 elements which are one element is incomparable to the other two and the other two are comparable. Then, well, by just doing a little bit of analysis, you realize that this is going to be a linear sum of anti-chains. So you have several anti-chains and each anti-chain is below the other ones, you know, are just linear order as an anti-chain. As it's written, it's just a linear sum, according to some index set I, of anti-chains of maybe of different sizes, one on top of another. The fact is that if you don't have a copy of 1 plus 2, essentially the incomparability relation is an equivalence relation, or like literally the reflexive closure of the incomparability relation is an equivalence relation, and you can partition your set into maximal anti-chain, your partial order into maximal anti-chains, which will be linearly ordered. So that's the first observation. And now, as an easy corollary, if you also do not have a copy of the free elements anti-chains inside your poset, then all these anti-chains might be a size at most 2, either of size 1 or size 2, because you don't have anti-chains of size 3. And so that's an easy corollary. And if for moreover you ask that, well, this is another property that we need. We were able to prove this. I mean, we already knew that the sum of 2 better partial orders is a better partial order, but actually you can prove that even the well-ordered sum of better partial order is a better partial order. And this you can do in the weak base theory RCA naught. So you take several better partial order, pi indexed by sign I, and this I has a well-ordered relation on it, so that you are doing a linear sum, which is actually a well-ordered sum. If all of the summands, let's say, are better partial orders, then you still get a better partial order. And this is something that we can prove in RCA naught. So putting all of this together, these are sort of more combinatorial observation. What we get is the following theorem. Suppose we have a theory which extends RCA naught, but it's not enough, it's not strong enough to prove that 3 elements anti-chain is a better partial order. By what we said before, also it does not prove that 1 plus 2 is a better partial order because those two are equivalent. And you take a finite poset P. Let's do first the finite case. Then T proves that P is a better partial order if and only if P does not contain 1 plus 2 and 3 bar as the suborders. These are the only abstractions, basically. And this is the case exactly when P is a linear sum of anti-chain of size at most 2. Here I can talk about a linear sum because P is finite, so the sum I'm doing is finite. It's saying linear or well-ordered is the same thing. So I'm just saying it's a linear sum. So essentially here, T will be able to prove that a finite partial order is a finite poset is a well partial order if and only if it is a sum of things like 1, 2 bar, 2 bar, maybe another 1, 2 bar, all put in a sort of linear way like that, you know. So 1, then maybe here there are 2 elements which are incomparable. Here there are again 2 elements. Here there is 1, 1, 2. So this one, for example, will be something that actually is a well partial order, even in a theory such as AC0 plus that does not prove that 3 is a BPO and nothing more. Because anything which is not of this form, if it's finite, it will contain either a copy of 1 plus 2 or a copy of 3 bar, and we know that these theories cannot prove that those are better partial order. Obviously, we are using the fact that a suborder of a better partial order is a better partial order. This is about finite better partial orders. So what about infinite ones? If we take an infinite partial poset, what can we say about the situation in a theory that does not prove that 3 is better partial order? Here we have to be a little bit more careful in the statement, basically. I mean, the idea is the same, but we need to be a little bit more careful in the statement. I do this for ACA0, but the first observation, before even going to the details of what I'm saying here, is that we can extend this to any other theory T that does not prove that 3 is BPO. Now, if you notice in the second point, I'm mentioning epsilon naught because I'm dealing with ACA0, and epsilon naught is the proof theoretic ordinal of epsilon 0. So if we use some other theory, we will have to substitute epsilon naught with the appropriate proof theoretic ordinal of that theory. So that's the first observation. Now let's look at what happens. We have a countable poset P, which lies outside the, let's say, subsystems of secondary arithmetic. It's just a countable poset, right? And we want to say, when is it provably a better partial order in a theory such as ACA naught? So statement one, which I have here, is just, well, the version for partial order and better partial order, sort of usual definition of what it means that an ordinal is provably well ordered in some theory, right? We say, well, we can find a computable presentation of that poset, let's say P0, and ACA0 will be able to prove that this P0 is a better partial order. So we computably have a computable copy of P, and ACA0 realize that that is a better partial order. On the other hand, condition 2 is a little bit more complicated than what we get when usually we deal with this sort of things with respect to well orders, and I will explain why. So what is 2 saying here? So we say that P is isomorphic to a computably enumerable suborder of 2 times omega, 2 times gamma for some gamma, which is strictly smaller than epsilon naught. So gamma is an ordinal which is smaller than epsilon naught, and we figure that epsilon naught has been represented in some standard notation system, so that gamma inherits this presentation there. And 2 bar times gamma means, well, just gamma copies of 2 bar, one on top of another, just gamma many copies of 2 bar. So this is a well-ordered sum of length gamma, which in a theory such as the ACA0, we know it's a well-ordered because gamma is smaller than epsilon 0. And we replace each element of gamma with a 2 elements anti-chains, basically a copy of 2 bar. We have to ask this to be computably enumerable suborder, because when we deal with well ordinals and the linear orders, we do not do that. We just say that well, P is just isomorphic to some gamma for some gamma less than epsilon 0 if we were talking about some linear order. The point here is that in the linear case, computability comes for free. Why does it come for free? Well, basically because any suborder of gamma, let's say, which is a well order, is actually isomorphic to an initial segment of gamma, because this is a property of well orders, and an initial segment of gamma is automatically computable because it's just a set of elements which are below some other element, right? The first element which is not in there. And while here we have to ask for computability, because by taking a suborder and playing where there are a real antichain with 2 elements and when there is just a single element, you can code complicated things in there. So it's not true that any P which is a suborder of 2 bar times gamma is actually a computable and enumerable copy, because it could code inside itself by alternating these 2 and 1s, basically some like 0 prime or something like that. So we have to ask for some computability condition, and that's the reason why we get a little bit more complicated statement, but it's sort of unavoidable because of the structure of this partial order. But this theorem is actually characterizing exactly what we can do, for example, in ACA naught, and a similar statement will hold for ACA 0 plus, substituting epsilon naught with a proof theoretical ordinal of ACA 0 plus, which is the first fixed point for the epsilon function, actually. Okay, so this is about provable better partial orders, and as I mentioned before, using these results, we were able also to get some results about the minimal better-Array lemma. So I will tell you something about the minimal better-Array lemma, which, as I said already before, is a basic technique in better partial order theory. It's the main tool very often to show that something is a better partial order, is to use to show this minimal better-Array lemma, which is saying basically that if you have a bad array, which you don't want in a better partial order, then there will be one with extra properties, this minimal bad. And then you argue from there for showing that cannot be anything like a minimal bad array into that partial order. And so you get then there is no bad array whatsoever. So what are the definitions here? Well, to simplify a little bit our presentation here, I notice this. If I take a P array F, so B here is a barrier which goes into B, or even if B is just a block, that will be enough. We can identify this P array with a continuous function. That's a different way of presenting a better partial order, to look at continuous functions. It's a little bit more delicate if you want to do into a subsystem or second order arithmetic, so I prefer the more combinatorial presentation, but this is easier if you work outside of them. So you take the union of B, all the elements which are mentioned in B, which is one of the conditions on being a block or a barrier, it's an infinite set, and you look at the function that associate to any infinite subset of that some P. Basically, you look at the unique initial segment of the elements of union of B, infinite subset of a union of B, which is inside the barrier, and that will tell you which element of P you can associate. This turns out to be very easily a continuous function because there are this finiteness condition on deciding what is P. On P, I'm just putting the discrete topology. So I'm just asking that the pre-image of any element of P is an open set in the collection of these infinite subsets of union of B. And you can turn also things around. If you give me a continuous function from some the collection of our infinite subsets of some infinite subset of n, let's call it V, then we can find a P array, at least on a block, and working a little bit more and using WKL not actually on a barrier, such that that block has union, the union is exactly V, and if you go back, you get again the big F you started from. So it's essentially the same thing. So I'm abusing terminology from now on, and I call such a big F also a P array, because I identify that with the P arrays defined on barriers. And then we can say that such an F is bad if for each infinite subset of V, f of x is not below f of x minus. So we are taking off the least element from x to get x minus, and we are applying the same function also to f. And WKL not, as I mentioned, is proving that P is a better partial order precisely when there is no bad P array in this new sense. So let's imagine that we are in WKL not, or we have to be a little bit more careful if we are just in RCA not, but essentially we are working there. And with this notion of P array, we can give a definition of a minimal bed array and state the different forms of a minimal bed array lemma. So it's minimal in which sense? You add to the partial order another partial order less than or equal prime, which is well-founded. You ask for that to be well-founded, and this is called a partial ranking if it's compatible with the original partial order you have, in the sense that if P is less than or equal prime to Q, then P was already below Q according to the previous to the partial order itself. So you are ranking all elements in P according to how far they are in this well partial order, which has a natural notion of rank, and we call that a partial ranking. Now we say that you have two P arrays and you want to compare them. One has domain this set V, or more correctly, the infinite subset of V, and the other one G has as domain the infinite subset of W. Now you ask that V is a subset of W. If you want to say that F is less than or equal prime to G, you are asking that on any input which makes sense for both functions, so any infinite subset of V, which is also an infinite subset of W, since V is a subset of W, f of x will be less than or equal prime of G of x. And we say that f is actually strictly below G if f of x is less than or equal prime to G of x. Now, f and G are just P arrays, but if f is bad, if G is bad, we say that this is minimal bad with respect to this specific partial ranking we are looking at, if there is no bad P array below it, strictly below it, according to this partial ranking. So you cannot go farther down according to this partial ranking. And the minimal bed array lemma is essentially saying that if you have a bed array, then you can get a minimal bed one. And we want to look at two of these. So the full minimal bed array lemma, let's say, is you have a partial ranking of P, and then for any bad P array, if obviously then this P is not a better partial order, you have a minimal, you have a bad P array H, you can go down below H, find some G lesser than or equal prime to G, which is still bad, and it's also less than or equal minimal. So in some sense, it's minimal with respect to this ranking. This is the more natural statement of a minimal bed array lemma. I think it can be found, for example, in Simpson's presentation of better partial order theory. This was this idea of a minimal better lemma was extracted from the first proof about better partial orders by Nash-Williams and also by Lever. I think Lever extracted already some form of this. Then we can look at this sort of weaker version, noticing that every well-founded poset is actually a partial ranking of itself. If P happens to be well-founded, then you can take as a less than or equal prime just less than or equal P. I mean, there is obviously satisfy the condition I wrote here. This condition here is trivial if you are the same relation. And if it's well-founded, then you're already there. So in this case, if P is well-founded and it's not a better partial order, so there exists a bad array, then there exists a minimal bad P array with respect to that ordering. So this is a weak form which is actually sufficient in many specific applications. So actually in another work, we proceeded a little bit ours. Freund, Pacomov, and Soldat studied these different forms of a minimal bad array lemma, and actually were able to prove that the minimal bad array lemma is actually equivalent to pi12 comprehension. So pi12 comprehension here is a very, very strong system of second order arithmetic, which is there are very few examples of statements which are equivalent to pi12 comprehension, and they were able to prove that both the full minimal bad array lemma and this weak form of a minimal bad array lemma are equivalent to pi12 comprehension. But notice that the base theory for this equivalence is actually ATR naught. So you already assume ATR naught, where you can develop some, sort of basic theory of better partial orders. And over that theory, you prove that MBA and MBA minus are both equivalent to pi12 comprehension. So obviously one wonders, can we weaken this theory? It's possible to get it down, well, ideally to RCA naught. And using our results, actually, we were able to prove that for MBA minus, this is not really possible. Because in RCA naught, if free bar is not better partial order, which is something that is compatible with RCA naught by Freund's result about free bar, then actually MBA minus will hold, because there are so few, I mean, the partial orders which are not better partial orders are very easily characterized as the one containing either 1 + 2 or free bar. And so you can actually argue on this and actually get MBA minus just because, well, there are just those, anything which is not a better partial order will contain a copy of that, and you can argue directly like that. So the consequence of this is that MBA minus will not imply ATR naught over ACA 0 plus, because if it were, if MBA minus will imply ATR naught, what we will get is that even in ACA 0 plus, where you know that you cannot prove that free bar is not the BPO, then you have models when ACA 0 plus holds and free bar is not a BPO, and where MBA minus holds, but these are models where ATR naught fails for sure, because free bar is not a better partial order, and so you cannot have an implication like that. So MBA minus really you cannot weaken much the base theory for proving free implies 1 in the theorem, which is on the top of my slide, because of this observation here. For MBA, the situation is probably different. We cannot say for sure that it's different, but MBA implies ACA naught over RCA naught. This is not still lowering the base theory there, because we get to ACA naught by this result here, while on the other end, we would need to get to ATR naught to fill the gap between the last theorem and the first theorem. So we don't know if using just RCA naught, we can get all the way to pi12 comprehension. We still have to fill the gap between ACA naught and ATR naught to do that. And we don't know if we are able to do that. So as you see, by playing with free bar and 1 + 2, we were actually able to get some results about the minimal bad array lemma. And I don't know how I am with time. Damir, tell me something, because if I have still a few minutes, I can sketch a little bit of a proof when 1 + 2 = 3, let's say, and try to convince you that it's an interesting fact. Or should I stop here?
5 more minutes, sure.
Okay. So yeah. I'm just sketching a little bit and giving you some ideas of a proof that 1 + 2 imply 1 + 2 better partial order. No, yes, implies that 3 is a better partial order. So this builds up on the main idea, actually, Freund's proof that free is a better partial order, free bar is a better partial order, implies they say not and they say 0 plus actually. So the idea by Anton was the following. We have a poset and we define another poset on what we can call the hereditarily finite sets with pure elements from P. So the hereditarily finite sets with pure elements from P has a quite natural definition, I think. Well, P are like that because these are the pure elements of our construction. And then if you have a finite set of elements which are hereditarily finite sets with pure elements from P, then also that finite set is going to be a new set into that construction. So this is a quite standard set theoretic construction. We can say you're starting from elements of P and building finite sets and finite sets of sets you built before and so on and so forth. The relation is quite, obviously it's quite important what relation we put on this set. So on the elements of P, we just copy the obvious relation, which was already on the poset P. When we have to compare an element P, so P and Q here are always elements of a poset, while I and B are sets, which occur in this construction of the hereditarily finite sets. So when P is less than or equal to A, well, if you can find an element in A is a finite set such that P was already below Y. And when A is below P, well, for every X in A, X is actually below P, below a single element P. So you allow even a finite set, which might be quite large in some sense, to be below a single element of P, because all the elements that are occurring in this set essentially are below P in the original construction. And then you have also to compare two finite sets, A and B. And in this case, you do what is quite known. I mean, it's one of the standard partial orders you can put on sets, which is every element of A is below some element of B. And well, this definition is quite set theoretic, presented this way, but actually you can formalize it in RCA not because you can represent the element of this HF of P as finite trees just with the leaves labeled with elements of P, which are the original UR elements, let's say. And this allows to define HF of P and also the ordering. I forgot to write the ordering here, the partial order in RCA not without any particular problem. And one of the main results in Freund's paper is that in RCA not, you can prove that if P is a better partial order, then this structure HF of P is also going to be a better partial order. And he used this, for example, to prove that a free bar is a better partial order implies AC 0 plus. But we can use it also for doing our construction, that 1 plus 2 is a better partial order, then 3 is a better partial order. Why is that? Well, if 1 plus 2 is a better partial order, by the theorem I mentioned before by Anton, we get that HF of 1 plus 2 is a better partial order. And so inside HF of 1 plus 2, we have to look for a copy of free bar, essentially. And it's not difficult to find it. Actually, we can find much more. So essentially, what we can find in HF of 1 plus 2 are two copies of the natural numbers, which are in some sense interlocked. So first of all, let's fix some notation about 1 plus 2. 1 plus 2 consists of a single element, which is incomparable with everything, and it's our element star here. And then two elements which are comparable between them, which are 0 and 1, with 0 obviously less than 1. So that's our notation. And now for every natural number, I define recursively elements in HF of 1 plus 2 in the following way. N dot is a star, 0, and then all the m dots for m is smaller than n. So 0 dot is just star and 0, and then I will add 0 dot to get 1 dot. It's similar to the sort of von Neumann construction, but I have these UR elements, star and 0, which are in any dot of any natural number. And I do essentially the same with double dot, just that instead of starting with star and 0, I start with star and 1. So I have 1, 1 is larger than 0, it's something larger. And then it's quite easy to prove by induction, and all of this can be done in RCA not that, well, first of all, the dot copy and the double dot copy of the natural numbers really are copies of omega. So m less than or equal to n, if and only if m dot is less than or equal to n dot. And the same for double dots. So I have two copies of the natural numbers here, which go like that. This is the dot copy, and this is the double dot copy. And these are related just in one way, that the 0 here is below the 0 here, the 1 here is below the 1 here, the 2 here is below the 2 here, and so on and so forth. But, and so that's the last condition here in my thing here, that m is less than or equal than n, then m dot is less than or equal n double dot, even when m equals n. While on the other end, the element in the double dot copy of a natural number are never below any element of a single dot copy. And once you make this observation, then it's easy to find some sets which are pairwise incomparable. For example, 3 sets which are pairwise incomparable. Here they are. For example, 0 double dot with 5 dot, 1 double dot with 4 dot, and 2 double dot with 3 dots. So the idea is we are increasing the double dots and we are decreasing the dots, and in such a way that the double dots are always below the dots. And why these 3 are incomparable? Let's check, for example, that the first set is incomparable with the last one. So the first set is not below the last one, because 5 is so large that it's neither below 2 double dot nor below 3 dot. So you remember, for a set to be below another one, we ask that every element in the first set is below some element in the second one, and 5 dot has no this condition. And the last set is not below the first one, because 2 double dot is not below 0 double dot, because 2 is larger than 0. But a double dot is never below a single dot. So 2 double dot is not even below 5 dot. So, and you can check also with the middle elements, the idea is the same. So we have these 3 incomparable elements. And we know that HF of 1 plus 2 is a better partial order. So its restriction to these 3 elements will also be a better partial order, but this is clearly isomorphic to 3 bar. So by playing this trick, we are able to show that 3 bar is actually a better partial order. Obviously, the big part of the proof, which I sort of hid, is showing that if P is the theorem by Anton that I showed here on the bottom of my slide here, that this operation of doing this hereditarily finite construction with your elements preserves better partial orders. That's really the key of the thing. And then you do something like that, and you notice this, and so you prove that 1 plus 2 equals 3. And I hope you are more impressed by this than my daughter was. And I'm ending my talk here. Thank you very much for listening.